Hello everyone, I'm Dr. Hussain Haydari, and today we're going to continue our discussion on polymers. Where we left last time, we discussed the three main processes and phenomena that happen in polymers, mainly regarding their phase changes. So we discussed crystallization, as well as melting and the other process, glass transition, and we looked at how these two processes are different. We talked a little bit about different types of polymers and how some go through that glass transition and some don't, and how it could be very important in terms of processing these polymers to know whether at room temperature they're at a glassy state or a deformable ductile state. And so we will look at how we're actually going to be utilizing this glass transition temperature and the melting temperature in processing these polymers when we actually look at different manufacturing processes, which will be during the course of next week. But today we're going to complete our discussion on the mechanical characterization and behavior of polymers, talking a little bit about fracture and failure in different polymers. So we already looked at the stress strain curve, the characteristic of every sort of material, which is basically the stress strain curve and the mechanical ultimate strength, the elasticity, the elastic modulus, and the elongation. Today we're going to specifically talk about that point of failure that happens in polymers. So to do that, let's first look at different modes of failure. So this corresponds to the same plots that we saw earlier in the previous lectures. Some materials actually have a brittle failure, and some have a ductile mode of failure. In the brittle case, as we've seen before, you have a stress strain curve that actually just goes up, up, up until it fails, and it doesn't actually go through that necking step. In contrast, ductile failure is the case where you actually have this necking, and you can see it kind of in these 3D renderings, that the material has sort of gone through this necking process, and the intersection at which the failure has happened is reduced quite significantly. And so it's as if you were stretching chewing gum or another sort of rather elasticy material until it failed. And this is basically the two extremes, brittle and ductile, but there's also a case where it's sort of an in-between situation. So when it comes to polymers, thermosets are known as very highly cross-linked materials. They're known to be rather hard and brittle. It's usually irreversible cross-linking, like resins and other sort of epoxies have. And so they become quite highly cross-linked and therefore quite brittle. They do not soften, and I emphasize, when we first talked about thermosets versus we talked about thermosetting polymers versus thermoplastic polymers. We mentioned the main difference was that the thermoplastic polymers, as the name suggests, turn into sort of a plasticky behavior when you heat it up. Thermosets do not do that. So if you heat it up, you cannot really change the shape and then cool it down and retain that shape. It's a completely different way of responding to heat. So vulcanized rubber, epoxies, resins, they're all good examples of this. And these particular types of polymers have a rather brittle mode of failure. That's because they're really strongly cross-linked, and they act kind of like metals. In contrast, thermoplastics, which I mentioned, are known to be materials that, upon heating, become really soft and deformable, such as polyethylene, polypropylene, polystyrene. These actually tend to have a more ductile mode of failure. Now, it's again good to remind ourselves of what we discussed last time, which is depending on the temperature, you can see a transition from ductile to brittle behavior. So if you actually cross over that glass transition temperature and cool it down, it becomes rather, I would say, brittle. So again, in terms of thermoplastics, you can also see the brittle failure mode, but that all depends on temperature. Also depends on the strain rate, as we discussed. So if you actually increase the strain rate, has the same effect as decreasing temperature. And what can happen is that you can potentially experience that brittle behavior and a different failure mode. So there's another rather distinct mode of fracture and failure associated with polymers, and that is known as crazing. Now, I will explain what this means, but basically you probably remember from when we discussed, this has been kind of the common piece of knowledge that we've held in these different lectures, and that has been sort of the polydisperse nature of polymers, the fact that they have both crystalline and amorphous regions mixed together. So you have some regions, you have crystalline structure, and then in between they're connected with these amorphous regions. So the fact that this is the nature of polymers means that it should somehow affect a lot of the other things. For instance, we saw that the melting doesn't happen at a certain temperature. It happens over a range of temperatures. Because of this sort of an statistical averaging behavior, you see that some regions melt faster, some slower. Now, similarly, when it comes to failure, if we've already seen that highly cross-linked and crystalline materials behave differently from amorphous materials, you can imagine that this would cause sort of a localized distinct behavior in a semi-crystalline polymer. So this is exactly what this mode of failure is telling us. This is a schematic showing what happens, and that is you can see these microvoids, and these happen in the regions where they're more prone to failure. So, for instance, these amorphous regions here, what happens is that you have one nucleation site for a crack, and that nucleation site typically happens in those regions that are, you would say, more prone to failure. In this case, the crystalline regions are quite strong. So typically that is where the failure nucleates. And what happens is that it stretches until these crystals expand and no longer can withstand the amount of stress exerted. And so you kind of see these bridge regions, these fibrillar bridge regions, can no longer take that load, and they all of a sudden tear apart. So this particular behavior that you observe in polymers is because of that natural polydispersity, and you don't see it in a lot of the other materials. And this, as you can see here, obviously happens in semi-crystalline polymers. A lot of the thermoplastic polymers have this sort of behavior. So now I'm going to talk about diffusion, and there's a lot of text in this page. We'll try and go through it. This is a really important topic. It doesn't have a lot to do with the stress, strain, behavior, and failure. We've already completed that part, but this is another sort of a physical, both physical and chemical aspect of the behavior of materials, and this fits in here, although it belongs to the previous chapter, chapter 14, but it's more relevant to our chat on the mechanical aspects of a polymer structure. So diffusion is basically the passive transport of molecules across a wall, a certain solid interface. It could be also a liquid interface or even a gas interface. But basically, it's the transport of molecules that happens passively rather than with a flow and active sort of perfusion. This happens rather passively through a particular interface. Now, diffusion, as with any other material, also happens with polymers. So you can have molecules that are trying to actually cross a polymeric wall and diffuse through. And so what we're going to talk about now is what defines how fast and how easy they can move through this wall. So what happens is that you've got these molecules, rather small molecules. That's the majority of our molecules that we're interested in are like oxygen, carbon dioxide, and in a moment you'll see why we're interested in this. So these molecules want to cross through your polymeric network, just like they would want to cross through any other material and get to the other side. So what we're trying to study here is how fast they can move through the polymer to the other side. Now, first of all, there's a chance that they cannot move at all, right? If the polymer is impermeable, we don't have a perfectly impermeable material, but if, let's say, theoretically it was, these molecules couldn't even get through. But it's always a range. So no 0% permeability or 100% permeability. It all depends on how fast and what content of molecules can get through. So this is in general what diffusion means, is again the passive motion or transport of these small molecules or any other molecule through this particular medium. In this case, it's a solid polymer. It could be water, a liquid. It could be anything. So what we're studying is the diffusion of, for instance, oxygen or carbon dioxide through a polymer. Now, this phenomenon depends on both the molecule that's trying to diffuse as well as the medium, in this case, the polymeric network. So what does it really depend on? Well, you can kind of guess. If you have larger molecules, it's probably going to be harder for them to diffuse because they have lower mobility. If you have smaller molecules, it would be much easier for them to diffuse through the same pore sizes and the same networks because they're a lot more mobile. And so the size of these molecules matters quite a lot. The other thing that matters is the polymer itself. If you've got a network that has a lot of pores in it, so these polymeric chains actually have lots of gaps in between, it's going to be a lot easier. If it's cross-linked quite heavily, the stronger the cross-links are, the denser they are, it's going to be more difficult for the molecules to get through. Apart from that, if these chains absorb the molecules to themselves, meaning that there could be some sort of chemical interaction that sticks these molecules to the chains, then it will also reduce the passive transport or the diffusion flux of these molecules through the polymer. So the diffusivity D is the quantity that we use that tells us how efficiently this combination is going to diffuse. So the higher the diffusivity means that you're going to diffuse faster, you're going to get a larger flux. If the diffusivity goes down, means that that goes down. So, so this again depends on the size, but also the interaction. So if there is some sort of a chemical interaction that basically sticks these molecules to your mesh, then you have another sort of filtering that happens in the mesh, another sort of resistance to diffusion because of the chemical binding, or could also be physical binding to the network. So again, it's a multiplexed sort of problem that depends both on the molecule and the network. Now, this is the first piece of information that's really important. When it comes to polymers, diffusion happens more in the amorphous region, or in other words, the diffusivity or the rate of diffusion, the amount of flux that you get, is greater through the amorphous regions than the crystalline region. Now, why is that? Because typically the amorphous regions have lots more voids and imperfections, which leave room and gap for these mobile molecules to actually be able to squeeze through and find their way. If it's a perfectly crystalline structure, it's going to have a lot less imperfections, a lot less pores and voids for these molecules to pass through. Another important thing is that this diffusion, apart from the molecules getting through, can basically lead to the material swelling. It can lead to some chemical reactions and the degradation of the material. So it's not always a good thing. It actually is quite bad. So sometimes they functionalize the polymers, or they coat them with something that reduces the amount of diffusion. So now that we know what diffusivity is, D here, let's talk about permeability. Now, permeability is again very similar to diffusivity with a tiny difference. So permeability is the ability of these molecules to permeate through this, okay? So it depends not only on diffusivity, which is how fast they can travel through and the mobility through this network, but also on solubility. Now, solubility means how much of these molecules can actually get in these and mix within, or in other words, the limit to how much, this oxygen or CO2 or whatever molecule content there can be at the same time inside this mesh. Now, if this material is insoluble, even if it can diffuse fast, it can't even get in there, okay? So imagine two materials that have different phases and they can't mix, right? It doesn't matter if those molecules can actually pass pretty fast, they can't even get in there. Okay, so it makes sense that the permeability is both a function of solubility and diffusivity. So should be able to, first of all, get in there and, in other words, fill in those pores, and then have the mobility or diffusivity to pass through. If it cannot get in there at all, let's say these chains somehow rebel the molecules, what's going to happen is that they can't even get in the first place, let alone get through. So the permeability coefficient is the product of these two, the diffusivity and the solubility. Now that we've defined permeability as basically the ability of these molecules to permeate through this membrane or this interface, this is the important formula. The flux of these molecules through this interface is the product of that permeability coefficient and the pressure difference divided by the thickness of this wall or this interface or this medium. So let's see what this means. Well, first of all, this makes sense. If you increase permeability or the permeability coefficient, you get a larger flux. Yes, that's correct. If it's more permeable, either more diffusive or has a larger solubility, a greater solubility, then what happens is that this product will go up, and therefore you'll get a greater flux. Of course, if it's more permeable, you get a greater flux. So this is directly proportional to permeability coefficient. But what are these two? Well, let's start from the thickness. The thickness of this wall, of course, if you make it thinner, it's going to have a larger flux. If it's thinner, it's going to be easier to get to the other side because you've got a smaller amount of media material or intermediate interface to pass through. So if this is thinner, this delta X is going to be smaller. This side or the other side, the flux is going to go up. So that makes sense. What about delta P, the pressure? Now, that is the pressure difference between the two sides of this barrier. Now, what that means is that if you increase the pressure difference, you'll get a greater flux. Is that correct? Yes, because if you increase the pressure, it's going to make these molecules move faster, hit each other quite more frequently, and also have a lot more kinetic energy and momentum to actually get through this material. So if you pressurize this, what's going to happen is that you're basically pressurizing these molecules through that membrane because they're just randomly moving in every direction, right? Your sort of nominal average acceleration or momentum in each direction is going to be more. So if you basically pressurize, if this was contained within a container and you're pressurizing it, it would actually increase the amount of flux of molecules. Now, why is it that this entire slide exists in this lecture? Why is it that we care about this? It's because this, alongside the stress strain behavior, is a very important determinant of what polymer we use. Because a lot of these cases, we use polymers for vessels that contain a gas or another sort of molecule. And what we want to achieve is that the polymeric vessel can contain these molecules quite efficiently, meaning that the molecules don't diffuse out and the container goes empty, flat, pretty fast. We want it to be able to contain these molecules. So if the permeability is really high, that's not good. It's not a good container. It's not a good vessel. The molecules can escape quite easily through the walls. What we want is that the permeability is rather low, and so the molecules cannot get through the walls of your container that easily. So let's look at a practical example. So here you've got all the different polymers: polyethylene, both low and high density, polypropylene, PVC, polystyrene. And what you've got here is actually, first of all, well, the acronym, but different molecules, different gas molecules, oxygen, nitrogen, carbon dioxide, and water, in this case, water vapor, I believe. And what you're looking at is how fast these can pass through. Or in other words, you're looking at the coefficient in that formula, the permeability coefficient, P sub m. And this is the first part of this formula. You also need to know in your particular case, what is the pressure difference between, let's say, the inside of that interface or the inside of your vessel and the outside, which is the ambient. You also need to know how thick the wall of that vessel is. So if you know the coefficient from this table, and you also know the pressure difference and the thickness, you can figure out what the flux is. Now, I'm going to give you a quick example. So soda pops, they have a polymeric, a lot of the cases, they have a polymeric material. This in this case and in a lot of the cases, it's common to use PET, which is basically polyethylene terephthalate. So this one actually has a coefficient, for every gas it's got a different coefficient, but for CO2 it has 0.23. Now, what it's asking is if it has an internal pressure, and note that it's a partial pressure, meaning that they've already calculated what the fraction of the pressure is that is associated to this molecule. Now, if you're not familiar with that, you should go back to your physics and chemistry courses. Inside a mixture of different gases, each gas has a partial pressure. And so what they're telling you is that the partial pressure associated with CO2, they've already figured out it's 5 atmospheres. So you don't need to do any calculations there. It's telling you that this is it's a pretty interesting example, because what we don't want is for that gas, the CO2, to escape your soda pop. We want it to stay in there for as long as it's on the shelf and it's purchased and it's used. So that fizz, the carbon dioxide, it's got a pressure of 5 atmospheres. And what it's asking you is, does this fizz empty a PET soda pop faster, or does oxygen in a PP, in this case polypropylene soda pop, escape faster if the wall thickness is the same and the internal pressure in this case is different, it's 2 atmospheres? So we're going to use that formula. We're going to first find our permeability coefficients for each of these 2 cases. Then we're going to cancel out the delta X because the thicknesses are the same. And we're going to look at the pressure difference. So it's a pretty simple question, but it's interesting. So first of all, the coefficients for CO2 and PET, we've got 0.23. For oxygen and polypropylene, we've got 1.2. And this is the unit here. It's a rather weird unit there. Just make sure that whenever you're doing the calculations, your pressure units, your volume units, or your length scale, everything is in one particular system. So don't take units from SI and mix it with imperial. Try and make sure that you cancel out the units together in a correct way. So first of all, we figured out what the permeability coefficient is. Now what we're going to do is, well, we know that delta X is similar. We're going to find the difference in pressure. So I'm going to just write that down here. So for the first one, the PET soda pop that has CO2 in it, we have 0.23 times the pressure difference is 5 atmospheres minus 1 atmosphere, which is your ambient environmental pressure. In case of the oxygen, it's 2 minus 1 atmospheres. And again, it's fine to use 1 atmosphere here. I am assuming that that is the partial pressure. You would have to calculate that for CO2 and oxygen to be precise, but here, just for simplicity, I'm assuming that they've both got 1 atmosphere. It's not super precise, but now I'm just trying to get the concept through that it's dependent on both the pressure difference and this coefficient. If the thickness was in play, that would also matter. So if you just multiply that and cancel out the other items, you would see that this one's 0.92 times 1 over D atmosphere units. This one's 1.2 times 1 over D atmosphere units. And what happens here is that you can see that easily the oxygen is going to pass through a lot faster. Well, not a lot, but by about 20-25% faster than the CO2 there. So again, I don't know if this actually has a practical use case, but what I'm trying to show here is that it's actually very important when it comes to containers, polymeric containers and vessels that are supposed to hold a gas content. Now, this is not just for pressurized containers and vessels, it's also for reactor vessels that have to sustain some level of a particular gaseous species, or it could even be for liquids, because a lot of these polymers could be permeable or impermeable to some extent to moisture. And so this is a very important consideration when it comes to the design and processing and selection of a particular polymer. So before we end, I'm going to have a few comments on the chemistry of polymers. We already discussed this in the previous chapter as well. Very briefly, we familiarized ourselves with free radical polymerization, and that is the process by which you conduct this propagation process through the activation via a radical. So what happens is that you have a photoinitiator that breaks into two free radicals. The free radical then reacts with this double bond here and opens it up. So one of the carbons is now connected to a radical. The other one has a free electron ready to bind with something, and that is nothing but the next monomer. And this continues on and on until you get a very long chain and it propagates. The other way that this happens is condensation polymerization. Of course, this is one other way. There are also other modalities. But in this case, what happens is that the binding unit isn't this electron transfer, which happens with the, in this case, is the interaction between an H group and an OH group here. And what happens is that when these two molecules, these two sort of copolymer double monomers here react with each other, the H and OH are sort of dislodged here and form a water molecule, and these two are bind together. So what happens here is that, for instance, in nylon, it's a condensation polymerization process where there isn't a double bond to be broken. Instead, you actually swap these two. You have a water molecule going through condensation, and then these two monomers connect to each other. And so nylon indeed is sort of a, I would say, a two monomer content sort of material. And so now there is one piece that I wanted to add here. Now that we kind of are familiar with two types of chain reactions, is that at the end of this cascade of reactions, you have to terminate at some point. And so there is one step, which is the initiation, especially when we talk about free radical polymerization, which we already discussed, is when you trigger that first reaction, you break that double bond, and you start the basically the chain reaction. Propagation is that chain reaction where you continue the cascade and build up these long chains. The third step has to be termination. Now, how does termination work? So instead of this sort of a free electron radical species that has been produced again by or from the reaction of a radical with this monomer, reacting with another sort of an unsaturated monomer, you have two of these radicals reacting with each other. And then when they react with each other, you've got a terminated species here. So they combine. Okay. There's also a chance that this can happen, this proportionation, but basically disproportionation is a lot more complex. What determines whether it's disproportionation or combination? But this is the main class that we're going to look at specifically when they study a cascade of reactions. It's not just these reactions that you see here. There are now at least 10 other reactions here that happen. For instance, it could be that this reacts with another radical and terminates. it could be that the radical reacts with oxygen and it quenches it and it's done. It could be that a broken oxygen can react here. And there are, you know, many different reactions that can happen in the duration of this cascade of reactions. But these are just the main ones that we're pointing at. So what you see here is that there is a chance that this propagation reaction can go on, and there is also a statistical chance that this radical can hit another radical and basically terminate the cascade of reactions. So that is when combination happens and you've got a polymer chain that's ready to go. So this is where we're going to leave it for today. For next week's lecture, we're going to start talking about how we're going to utilize what we know about the mechanical behavior of polymers, both thermosetting polymers and thermoplastic polymers, as well as elastomers, in order to design processes that can manufacture and shape these materials. So it's going to get really exciting. We're going to talk a lot about conventional manufacturing processes, but also about unconventional and modern manufacturing, additive manufacturing specifically, and we're going to look at the main processes there and how they have utilized these different properties of polymers in order to deliver sort of reformation and reconfiguration into a particular geometry and a particular application. So next week we're going to talk about processing of polymers specifically, but for this week we're going to leave it here, and I'll talk to you in the in-person lectures as well as the asynchronous lectures starting next week. Have a wonderful rest of the day. Bye.